Chapter 13, slides 11 through 17. Okay, so let's get into it. What can ethers do? Let's remind ourselves about the first set of slides in the ether chapter. Ethers are generally non-reactive. Therefore, there's not much we can do with acyclic ethers, right? So if I have something like diethyl ether, which is a great solvent, I need pretty harsh conditions in order to see some reaction occur. Okay, so the conditions have to be pretty harsh. And when we say harsh, we mean acidic. Okay, so if I were to do an SN2, I would use, say, a strong acid to make the oxygen into a better leaving group. And then if the only thing floating around is Br minus, then the Br minus performs an SN2 on that primary carbon. And we end up with the alcohol and the ethyl bromide. Now, this can be done again because now I have an alcohol under HBr conditions, which can get protonated. And so I end up with a second equivalent of ethyl bromide. So basically, you're just kind of tearing apart this ether and substituting a bromine on either side. Carbon 1, 2, 3, and 4. Carbon, we'll say 4 and 3. 2 and 1. Right? We end up with basically a torn apart molecule. This is not something that people want to do very often. We want to form bonds, form carbon-carbon bonds and build up our carbon infrastructure, not break it down like this. So it's very harsh, very impractical. And again, if you had a more substituted system, you would just probably employ more SN1 type conditions, which you always have to be wary of because, you know, E1, you have to be aware that it's always in competition with that E1. But technically, you know, one of these could leave. Doesn't matter which side you do first, who knows? You end up with an alcohol and, in this case, a secondary carbocation, which if bromine is the only thing floating around, you could force it to go. But it's in competition with getting reacted back with itself. So it's reversible because the oxygen could attack it and you could go back to the beginning. You can see that, you know, this isn't the best thing to try to do to an ether. You need very strong conditions. And at the end of the day, you get this hodgepodge of, right, different broken apart and potentially alkenes because of competition with E1, but broken apart molecule. All right, I don't find this very interesting. Let's go back to the interesting stuff. Epoxides. So let's just go back here for 1 second. Ethers, I guess the bottom line is they're great solvents because they're not really useful any other way. Ethers as epoxides, however, have tons of functionality. Because of the ring strain, they're more prone to open up. So let's just review exactly what we've seen in the past. So I forgot to write my review up here. Review, definitely. We've done this before. And so I'm simply emphasizing its importance in going through it again. if I started with an epoxide and I was working under acidic conditions, pick a solvent, any solvent, H2SO4. And pick a solvent, no solvent or ethanol or water. I don't know, I'll do methanol. Okay, so a solvent, a protic solvent in an acid, you're going to do acid-base chemistry first. The epoxide gets protonated, activating it. It's now bridged and charged. So what it's doing here is the dipole is now going to change given the bond elongation. So one carbon is now more electropositive because the oxygen starts to move away. You evaluate what solvent, if any, given, and we chose arbitrarily. We had decided, oh, let's do methanol. The methanol is a weak nucleophile. It's going to attack the carbon it's told to because of the epoxide's in charge. Get it? In charge. It's charged and bond elongating, and so it attacks from the bottom, from the opposite face, and opens up the ring-strained epoxide. Giving us this system here. And like always, we're done and we just need to work it up. We're going to use a little bit of base to take off the extra proton. Workups are always acid-base chemistry in this case. And we end up with, oh look, an ether. By using an alcohol solvent here, I ended up with an ether functional group and an alcohol functional group. So 2 functional groups on the molecule. You guys can practice doing these with, any variation of acid and solvent or no solvent. Interestingly, our body uses epoxides. You do see epoxides in a lot of different places in nature. Squalene is a molecule that, gosh, our skin makes. It's also a molecule that's generated, I believe, in the liver. Lots of organisms generate squalene. Squalene is a foundational terpenoid molecule that biological systems make, and it's a precursor to making steroids in our body. One of those steroids is cholesterol, shown here. You can see, I always say, you can tell a steroid, no matter which it is, it's got the 6, 6, 6, 5 system, right? So that's very classic for a steroid. And steroids are made from this long chain squalene molecule. It's just carbons and hydrogens. Now here's the beauty of our body. This is how specific our body is that it has an enzyme called the squalene epoxidase enzyme. And what's so magnificent about this enzyme is, count them up. We got 1, 2, 3, 4, 5, 6, 7 alkenes in this molecule. And you know what? Only this one gets epoxidized. So that squalene epoxidase enzyme, it has a shape and a very complex pocket. This molecule squalene fits in there, and then the epoxidation occurs, and because of how it's situated within this beautiful enzyme, you only epoxidize one of those alkenes very specifically. So this is a very chemoselective epoxidation because you have lots of alkenes to epoxidize, but only one of them reacts. So you can see that right here. Okay, well then what? Well then, through the activity of what's around, it kind of cascades into a process of ring opening. So this epoxide is what gets the reaction started. So you can think of it this way. Think of it as the pi electrons right on the next double bond. Look at that. If that had, you can see I'm kind of tracing where the new bond should be. That would make a perfect six-membered ring. And we know six-membered rings are nature's perfection, right? Bond angles are beautiful. There's no there's no torsional strain. There's no angle strain. There's no ring strain in a six-membered ring. So the way that a squalene molecule is set up is that that next double bond can perfectly be used as a nucleophile to open up. Do you see that? Ultimately, the oxygen gets a negative charge, but gets protonated because, you know, we're in the body. And there we go. We made this molecule. Oh, but don't forget, carbon 1, carbon 2, carbon 1, carbon 2. If that bond opens up to make the bond, carbon 1 now has a positive charge. But oh look, isn't that beautiful? There's another pi bond just perfectly away, which can open up. Right, carbon 1, carbon 2. Beautiful. And then if, let's call this carbon 3, 4, 5, and 6. 3, 4, 5, and 6. If the 5-6 double bond is what breaks, right? 5-6 double bond breaks, then carbon 5 has the positive charge. But oh look, there's another gorgeous six-membered ring to be made. Double bond, perfect situation. And you can see that it just keeps cascading. One bond opens up. Right? And now there's your double bond. So our carbocation. But now the double bond that's nearby, when it forms, is going to form a 5-membered ring. So you can start to see how this is a precursor to many, many, many steroids because it builds the 6-6-6-5 orientation with the oxygen in that perfect position. And ultimately, the side chain. So this is why I have many arrows here, because getting to cholesterol with the other groups on it, you know, there are other processes that occur, but this is how our body gets the 6-6-6-5 system. It's effectively a cascade, and you could write it in one fell swoop. Really elegant, just beautiful. These are the types of biomimetic pathways that we try to recreate on our own when we're in the lab. We're like, oh, could we make a squalene? How could I epoxidize that one? I mean, because if we could elicit this one-step reaction, because this is effectively one step, it's a cascade, boom, 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 boom. All the rings are made all in one fell swoop. That is just an elegant way to synthesize something, making carbon bond, carbon bond, carbon bond, all in one pot. Nature is very, very good at it. All right, more review. we also talked about epoxides being able to undergo SN2 chemistry. And this was always a little easier because in SN2 chemistry, the epoxide's not in charge, your nucleophile is. And, you know, I could use something like an alkylithium, like I introduced in the previous chapter. The lithium is positive, the carbon is strongly negative. So the carbon's in charge. The epoxide sits equilaterally between the two carbons. Each carbon is equally partially positive. The one who's in charge, being the strong nucleophile, gets to decide which carbon to attack, and it does so avoiding steric hindrance. And I've made a new carbon-carbon bond because I arbitrarily chose to use the alkylithium as my strong nucleophile. And then we're done. There's a workup stage under acidic conditions to protonate the oxygen. And there you are. I could have changed this methyllithium all day long, right? I could use sodium methoxide. I could use phenyl thiol, or the deprotonated version of it, sorry. Right? I could use a Grignard, right? Strong nucleophiles, strong negatively charged systems. But that's review. I'm going to give you guys these reactions that you've seen before for you to practice some more. And there's further practice on the next slide. How do we open these up? Okay, so you've got some practice here. Pay attention to regioselectivity, which carbon it attacks, and also pay attention to stereoselectivity. Think about what kind of product mixtures you're going to get at the end. Will it be chiral or will it not be? I end this set of slides talking more about how epoxides can be used out there in the real world. And if you've ever thought about sterilizing equipment, say medical equipment, over the years, as we started to use more and more plastics and less metallic substances, you know, say, think about like your equipment that is made of a polymer that needs to have no bacteria in it, right? It has to be sterile, right? Comes in those packages and you peel open the package. How do you do that? You can't just stick those equipment pieces into an oven and burn off the bacteria at a certain temperature. I mean, most of those plastics will just degrade and melt, right? Or burn up. It'll start burning. So as we move away from metals, how do we sterilize those polymer type equipments? So ethylene oxide is the simplest form of an epoxide. It's just when you have two carbons and you make an epoxide with ethene, that is ethylene oxide. And it's a colorless, flammable gas, right? You can understand why. Very low molecular weight. Ethers are low boiling and so very high volatility. So it's a flammable, colorless gas. Now, what's interesting is that organisms, like bacteria or things that could be growing on something, they have DNA, and amines say, it's thought that like a portion of the DNA is involved in when exposed to this ethylene oxide, basically does this ring opening to give you the compound shown to the right. Now, what this does is that this process, if that's what's happening, if you're introducing ethylene oxide gas and there's bacteria there, the bacteria's DNA interacts with it, and this process interferes with normal function of DNA, thus killing the microorganisms. So this is also very nice too, because the gas easily diffuses through the porous materials, effectively killing the microorganisms through this pathway that I'm just showing you. So basically, this ethylene oxide gas is sold as a mixture, 90% CO2 and 10% ethylene oxide. And what this does is it cuts down on the explosive, flammable nature of it so that it can be exposed to air without danger of explosions. And it's sold as, it's called carboxide. That's what it is. But it's 90% carbon dioxide, 10% of this ethylene oxide epoxide, and effective for disrupting DNA function in microorganisms.